Hello everyone. Today we are going to talk about conjugate gradient descent method for solving system of equation Ax equals to b. So, so suppose we have a system of equation Ax equals to b where A is a large, sparse, symmetric and positive definite. So this method is particularly useful because it doesn't require any to invert A matrix A, which would be computationally expensive for large system. Let's break it down. In any system Ax equals to b, we are trying to find the vector x that when we multiply by a gives us b. Think about x as a point in a space, uh, and our goal is to move through the space to reach the point that minimizes the error or residual r equals to ax minus b. So the difference between our target b and our current approximation ax. So the conjugate gradient method use the idea of the steepest descent or always moving in the direction where the error decreases the fast. But pure steepest descent method can get inefficient because it sometimes oscillate and doesn't converge quickly. So the conjugate gradient method refines this by ensuring that each new direction will take is conjugate or orthogonal in a sense that align with the properties of A. So this conjugate relationship prevent the oscillation of our steepest descent and allows us to take the direct path towards the solution. So the algorithm is we have to initialize the initial we first we will initialize the um, our first point that is x. So initialization will be x naught and compute the initial residual that is r naught equals to p minus ax naught. And next we will find the first direction p naught, which is r naught. Okay. So then the iteration will start for in the iteration part for each step k, we will compute the step size alpha k that minimizes the error along pk. So we'll compute the step size alpha k that minimizes the error along pk. And this alpha k will be rk transpose rk divided by pk transpose a pk. And we will update the next step xk plus 1 equals to xk plus alpha k into pk. And the updated residual will be rk plus 1 equals to rk minus alpha k a pk. Now we determine a new direction pk plus 1, ensuring its conjugate to previous direction. This direction calculated with beta k equals to Rk plus 1 transpose Rk plus 1 divided by Rk transpose Rk. And we will set Pk plus 1 equals to Rk plus 1 plus beta k into Pk. And we will now we will repeat these steps until our Rk become very small or reaches to a definite tolerance level that's given by the users. So in this way, each new search direction is a combination of the residual and the previous direction, ensuring the direction are conjugate and eliminating the need to go back to any earlier step. So why this method is efficient? I mean, there are several methods to solve Ax equals to B solution, but this is efficient because uh, because the conjugate gradient only requires matrix vector multiplication only, which is computationally cheap for sparse matrices. Also, this method typically converges in at most n step for an n cross n matrix. Uh, Often it can converge faster also. So the sum of to sum up the conjugate gradient method is powerful because it efficiently navigates the space of possible solution by combining the principles of steepest descent with the orthogonality of conjugate direction. So this gives it both speed and stability when solving the large system. Thank you.